Well, hello guys, here Mr. G with another video for the grade 12. This time we're going to be answering question 6 from the mid-year diagnostic exam done in the Northern Cape in 2023. This one is about equilibrium. The question says pure hydrogen fluoride is sealed in a 2 decimeter cubic container at 293 Kelvin. The reversible reaction reaches equilibrium according to the following balance equation. You have this balance equation and they are telling you that delta H is positive 542 kilojoules. It means if it's positive, that is already telling you that the reaction is going to be endothermic. Okay, so let's write that one here. But that reaction is the forward reaction. So the forward reaction, I'm going to do it with an arrow, is endothermic. Remember, for equilibrium, you need to know this one, because if it's endothermic, an increase in temperature will favor that reaction, okay? Now, define the term chemical equilibrium. Now, chemical equilibrium is the state where the rate of the forward reaction equals the rate of the reverse reaction. And careful, because some learners attempt to say forward equal to backward or reverse, and it's not like that, it's rate. So be careful with that one. There are some important words there, okay? So it's when the rate of the forward reaction equals the rate of the reverse reaction. How does the rate of the forward reaction compare to that of the reverse reaction before equilibrium is established? Choose from greater, smaller than or equal to. And that one is quite simple. At the beginning, they said before it reaches equilibrium, which is at the beginning. At the beginning, only the forward reaction is very, very fast, because all the reactant, which in this case is HF, is producing or is working to produce the product. So the rate of the forward reaction is very fast at the beginning before it reaches equilibrium. Redraw the following set of axes in your answer book. On the same set of axes, draw the potential energy diagram for this reaction. We say previously that the reaction is endothermic, guys, and you know the endothermic reaction, you start at the bottom with some energy, you go out all the way up to activation energy, and then that will be the graph they want there. So this is the graph. They say indicate the following: the activation energy for the forward reaction. So here the activation energy, guys, first, you must know that this one is the reactants, there on the left, and the on the right is the product. Now, the activation energy, guys, is going to be the distance from the energy of reactants to the activated complex. All this energy here, from here to there, is what we call activation energy. And we can say EA, for instance, in this case. That is the activation energy. The value and sign of the heat of the reaction for the reverse reaction. Be careful now here. Now, the change in enthalpy, which is the heat of the reaction, this is quite important, is the same for the forward and the reverse, which is this distance here. The distance between energy of reactant and energy of product. This one here is the change in enthalpy. Alright, that is the heat of reaction. Let's write here heat. Heat, because that is the question. But now they want the heat of the reaction for the reverse. I said is the same, but it will be negative in the opposite direction, because it's the reverse. So it will be negative 542 kilojoules per mole. Okay? Note that is the heat of the reverse reaction. I don't want you to get confused. And the final thing you must indicate is the activated complex. Remember, the activated complex, guys, is this unstable point that is the highest energy, and this is the activated complex there at the end. That's it. This is the question. This is what they asked. That is the graph is a very important graph. It should be in the exam. Question 6.4. At equilibrium is found that 0.05 mole of F2 is present and in the container. Calculate the initial amount of mole of HF released in the container. The equilibrium constant is 3.5 at 693 Kelvin. Okay, I isolate the question on this side so we can answer this one. Okay, now for this one we are going to use the right table. Now for the right table, remember you have the reaction or ratio, which we are going to real fast write it here. So I'm going to do the following. I'm going to write reaction and then I'm going to write ratio. So isolate the ratio. I'm going to do it very slow, guys. So there is 2 for here, there is 1 for there, and there is 1 for there. Then in the table you will have initial, and this initial is going to be in mole. All right, then you are going to have change, and this one is also going to be in mole. Then you are going to have equilibrium. Let's make it perhaps in capital letters. Equilibrium, also in mole, and then we're going to have once more equilibrium, but this is going to be concentration. So I'm going to write here equilibrium, but this one is in mole per decimeter cubic, guys. And this one, the formula we are going to use, this one is concentration is equal to number of mole divided by volume. This is the table we are going to use. This is the table you are going to use all the time to make this work easy. The table is not compulsory. You can do it if you want. You cannot do it if you don't want. It's entirely up to you. However, it helps to make the work organized in this specific topic. I'm just trying to draw the table to have it clear and organized and separate the different species here. Okay, there is my table. Now the question said, we're going back because we are not going to start completing that table. The equilibrium is at equilibrium is found 0.04 mole of F2 is present. At equilibrium, moles, not here, 0, mole at equilibrium. So we go to equilibrium moles and we have 0.05 of F2. 0.05 mole of F2. I'm not going to write mole because it is written here at the beginning. Okay, now they say is present in the container at initial amount in the container. The initial amount in mol F is present in the container. Calculated, didn't see this word. Calculate the initial amount in moles. So they want to know what is the initial amount in moles of HF. What was the initial? You started here with HF. Let's make that one an X. This is what they ask you in this question. They want to know what is the initial amount of HF. And they also telling you that at equilibrium the Kc for this reaction is 3.5. So at equilibrium here the Kc is equal to 3.5. There we go. That is all we have here. Okay, guys, that is what is given to us. So let's start now working with this table. Okay, now the first thing you need to know is that initially you don't have any of the products. So the number of mole of H2 and F2 is going to be 0. That is initially. You have nothing of the product, you only have the reactor. Now, if you at equilibrium you end up with 0.05, what was the change of S2? That was 0.05 mole. That was the change here for the F2. Now, in the change is the only place in this table that you are going to use the ratio. The ratio can only be used in the change. So the ratio here for H2, so I'm going to write here, for H2 to F2 is 1:1. Therefore, the amount of moles that is going to be here at the moles amount, because it's the change, or in change, the amount of mole that hydrogen changes, is going to be also 0.05. Okay? And now, guys, we're going to also use the ratio for the reactant, for the HF. So now the ratio here of HF to F2 is going to be 2:1. In other words, you'll have double HF. Okay, so in this, if we have 0.05 mole of H2, if we have 0.05, let's see how can I write it here in this little space there. I'm not going to write the ratio because you can see it, so I'm going to rewrite it. HF is to F2. The ratio is 2:1. So what will the number of mole, what will the change number of mole be if you have 0.05 here and you do a cross product? So the change here, number of mole change, will be equal to, with the blue one, this is simple cross product here, guys, and it's 2 times 0.05, which is 0.1. So here is 0.1. That was the change for the object here. Now let's go to the equilibrium. What happened if you have 0 and the change was by 0.5, but this one is positive because it is forming, it is a positive change? You will get here, which is 0 plus 0.05 or 0.05. But now here this change is negative because in actual fact the number of mole of the reactant decreases. It decreases because reactant is being used up. So what is going to be the change at equilibrium? I mean, what happened at equilibrium? What will the final amount of number of mole of the HF at equilibrium will be? X minus 0.1. This is important there. Okay, I hope you do understand, guys. Now, end of story. We have to calculate the concentration and the volume. Let me tell you, the volume is given to us at the beginning of the question. The volume was going to be, let me look, I'm looking here in my notes, 2 decimeter cubic. The volume is equal to 2 cubic decimeter. That is given to us. So we're going to calculate the concentration in each case. Concentration here is equal to number of mole divided by volume, the number of mole at equilibrium, right? So concentration is equal to X minus 0.1 divided by volume, which is 2. We go to each of them and we repeat the question here. Concentration is equal to 0.05 divided by 2, and you get 0.025 in each case because it's the same number, 0.025. Guys, the table is completed. We still have to look for X, so that is when the Kc is coming to play a role here. Now make sure you write the Kc expression first before anything else, which is very simple. Remember, it is concentration of product, square bracket is concentration, divided by the concentration of reactant. And in this case, you only place the gases and the aqueous solution. In this case, everything is gas. So the expression for this question here will be Kc equal to, let's go to the chemical reaction. The product is F2 and H2 with non-coefficients at the front. So is the product of H2, concentration of H2 multiplied by the concentration of F2. Okay? And then divided by the concentration of the reactant. The reactant is HF, and then to the power 2 at the front that you can see it there. So to the power 2, HF to the power 2. And guys, the rest is substitution. Let's move all these expressions the left a little bit. There we go. So now we're going to substitute what we have, and the case is 3,5 equal to concentration of H2 is 0,025 multiplied by 0,025 divided by x minus 0,1 divided by 2. Everything to the power 2. And then here are most of the mark of this question. This is only one mark you will get, which is for the final answer. Now, the best way of doing this one is to rearrange the equation and, for instance, say that x, you change in places, x minus 0,1 divided by 2. Everything squared is equal to 0,025 multiplied by 0,025 divided by 3,5. I swap places there. And then here you can find the square root on both sides, so that square is gone. That square is gone, and then everything is a linear equation here. Guys, it's quite simple. And when you do this calculation, which I trust you can do it, is now a very simple calculation, like really simple, you will get that x is equal to 0,13 mole. That is the answer for this specific question with the table. I hope you understand, guys, but you can write comments and ask questions if you don't. Okay, we are almost done with this question. The temperature of the reaction mixture is now decreased. How will this change affect each of the following? So now, if you increase in temperature, we're going back to the reaction. The reaction is endothermic. We already determined that. The endothermic reaction is favored if you increase the temperature. Alright? So if you decrease the temperature, which is what they did here in this question, I'm looking here, they say the temperature of the reaction is now decreased. Okay? Now, what happened to the amount of each gas? Okay, now if they decrease the temperature decrease, let's write it here. If temperature decrease, the reverse reaction is going to be favored. Alright, so saying that, what will happen to the amount of gas? This one will increase, so it's going to be more gas. This one will be less, and this one will be less. Okay, because it is a exothermic reaction. So now you know what happened to each of them and why. Let's go to write that one to explain the question. They say explain using Le Chatelier. So let's do it on this idea, 6.5.1, okay? And now for each gas, what happened to the HF? HF increases. What happened to H2 and F2? They decreases. Right? So you have to say HF increase, H2 and F2 decreases. Decrease in temperature favors the exothermic reaction. And then the reverse reaction is exothermic. Okay? So that is the question. Question 6.5.2, rate of the reverse reaction. Now the rate decreases. The rate decreases. It doesn't matter if is exothermic or endothermic or is affected by which rate. The rate is going to decrease. If you decrease in temperature, the rate decreases. But let's explain. They say use the collision theory to explain that answer. So we're going to answer right here after the calculation of the using the table. That is question 6.5.2. Okay, we said decrease. It has to decrease. If you decrease in temperature, nothing to say. The rate decrease of both forward and reverse. Now, how to explain this one? The first thing you have to say that decreasing temperature decrease the average kinetic energy of the particle. You should know that we did work a lot in rate of reaction. Then less particles will have sufficient kinetic energy. So less particles will have sufficient kinetic energy and therefore less effective collisions per unit time. And this is the end of that explanation. A decrease in temperature, remember here we are speaking about temperature, right? Decreases the average kinetic energy of the particles. Less particles having sufficient kinetic energy, less effective collision per unit time. End of this part. And then to end this question 6.5.3, how the decrease in temperature will affect the Kc value. We said that if we decrease in temperature, we'll get more reactants in this case than product. If we get more reactants than products, then the Kc value will decrease. Remember the Kc value, just for you to remember, is equal to concentration of product divided by the concentration of reactants. And now the concentration of the product is less, the concentration of product is less with this change. We spoke about that one in question 6.5.1, and the concentration of reactant is more. So when you look at the ratios here, then that Kc will decrease. Guys, this is the end of question 6. I hope it helped. It's a good question to practice. It's everything that could be asked in the exam. Next time we're going to be doing question 7, which is the last question of this amazing diagnostic. It is related to acid and bases. And then I'll see you next time. Don't miss out that video. Subscribe for the channel if you did not that yet. Thumb up. I'll see you next time. Mr. G here.